It's not just central angles that have a special relationship with arcs. Inscribed angles are important too. Well, they're half as important, as you'll find out. So let's talk about some definitions here. What do we mean by an inscribed angle, you ask? Well, it's an angle formed by two chords of a circle with its vertex on the circle. So here we have circle C, and angle P, or angle JPN, is an inscribed angle, since segment JP and segment NP are chords, and the vertex of the angle is on the circle. Now, an interesting thing happens. Notice the endpoints of the angle, J and N. They intercept an arc. So an intercepted arc is an arc with endpoints on the sides of an inscribed angle and all points on the interior of the angle. So notice arc JN is the intercepted arc. So now let's talk about some theorems. Here we have the inscribed angle theorem, and that says that the measure of an inscribed angle is half the measure of its inscribed arc. Get it? Half as important. A central angle and an arc measure are the same, but an inscribed angle is half the measure of an inscribed arc. Get it? Haha, half as important. That means that the measure of angle JNP is going to be half the measure of arc JN. There are actually three cases to this type of theorem, and each of them have to be proved separately. So case one is if one of the chords actually happens to be a diameter. In other words, the center of the circle is on one of the sides of the inscribed angle. Case two is if the center is on the interior of the inscribed angle. And case three is if the center of the circle is on the exterior of the inscribed angle. So there are these three cases. The theorem covers all three cases, but we're only going to start by proving the first case. And then you can prove cases 2 and 3 later. But they both revolve around the first case. So here we go. We have circle C with angle JPN inscribed in it, and segment PN is a diameter. So we want to prove that the measure of angle JPN is equal to half the measure of arc JN. In order to prove this, we are going to add in an auxiliary line, which is one of those lines that we add to help do things. In this case, segment CJ, which happens to be a radius of the circle. Speaking of radii, segment CP is also a radius of the circle. And since both of those are radii, we have triangle JCP that is an isosceles triangle, because the definition of a radius, actually it's the definition of a circle, all radii are congruent. Okay, so we have an isosceles triangle there. But before we move away from the picture, I have one more thing to add, and that is the definition of arc measure, which says that the measure of arc JN is equal to the measure of angle NJC. So remember, the arc measure is the measure of a central angle. Now back to our triangle. The isosceles triangle theorem then tells us that angle J is congruent to angle P. So the base angles of an isosceles triangle are congruent. The fact that we have a triangle allows us to use the triangle exterior angle theorem, which says that the measure of the two remote interior angles, J and P, added together, are going to equal the measure of an exterior angle. In this case, the measure of angle NJC. Can you see where we're going here yet? I'm trying to color code things to help you out. Let's use the idea that angles J and P are congruent and that their measures added together equal the central angle, and come up with this statement. Using the substitution property, we know that 2 times the measure of angle P is equal to the measure of angle NJC. So we replaced angle J with angle P, and then added the two angles together. But we want the measure of angle P by itself, which also happens to be the measure of angle JPN. So we're going to divide both sides by 2, and that will give us the measure of angle P is equal to 1/2 the measure of the central angle. And now we're done. Because if we take this equation and combine it with the equation in the yellow circle, using the substitution property of equality, the measure of angle P, which also happens to be the measure of angle JPN, is equal to 1/2 the measure of arc JN. Pretty easy to do, pretty quick, pretty simple. If it helps, formulate a T-chart proof from this flowchart proof or a paragraph proof. But right now, let's work out an example of using this. What are the values of the variables in this figure? I suggest we start looking at P here at the top, because you'll notice that that is intercepted by the 45-degree angle, this inscribed angle here, angle NPC. Since the measure of an inscribed angle is half the measure of the arc, that means that 45 is equal to half of P. Oh, wait a minute. If you multiply both sides by 2, you find out that P is equal to 90 degrees. All right, so we found P. Now we need to find Q. You'll notice that Q is the measure of an inscribed angle, and it intercepts this arc here, arc CN plus a little bit, this 34-degree portion here. So that means that Q is going to be half the measure of that arc, which happens to be 34 degrees, plus 90 degrees, that P there. So Q is half of 124 degrees. And of course, half of 124 is 62. So Q is 62 degrees. Right. A very easy theorem to apply. All that we're doing is taking the measures of arcs, dividing them by 2, or the measures of angles and timesing them by 2.